we were asked to look at these 4 problems, and we did the first one at the end of the last lecture. So let's get on the whiteboard here and let's look at these other 3. We'll break them down and try to make some sense of them. So the first one here, we have nitrogen reacting with oxygen to make nitrogen with oxygen to make Okay, so that's what you were asked to do. Now, to set it up, we needed to set up our atom economy by listing out, okay, I've got 2 nitrogen and 2 oxygen over here, 2 nitrogen and 3 oxygen over here. So right away, we're going to see that we've got a problem here overall. And that problem stems from the fact that we have 3 oxygens over here, but only 2 over here. The nitrogens right now are balanced, but the oxygens are not balanced. And we're going to have a problem with balancing in general because I've got an odd number on the one side and I've got an even number on the other. And there's no number I can multiply this O2 by to give me 3 that isn't a fraction. So when we face that situation, the thing to do is collective doubling. So I'm going to double the nitrogen. I'm going to double the product. That's going to keep my nitrogens still even at 4 apiece. But 2 times 3 is now going to give me 6 oxygens in total. And now I have a way of getting a whole and reasonable number here on the oxygen. 3 times 2 is 6 also. So that was one approach that you could take. Now, the other approach that you could have taken stems off of the trick I gave you last Friday, where we would have taken these subscripts, the 2 and the 3, and turned them into the coefficients, 2 and 3 over here. If we had done that, we would have ended up with 4 and 6 on the reactant side, 2 and 3 on the product side, which would have meant that we would have had to double the product, which is what we had to do it. So both approaches here end up working and giving us the same exact result. So that's the first example. In the second example, we've got aluminum sulfide reacting with hydrogen to make hydrogen sulfide, H2S, and aluminum metal. I guess that was gold, wasn't it? AU. It's AU, not AL, right? Right idea, wrong element. Regardless of whether it's aluminum or gold, setup is exactly the same. We can approach it in the same manner as well. Okay, so on one side, we've got our gold, we got our sulfur, we got our hydrogen. The other side, we've got the same thing, gold, sulfur, hydrogen. We have 2 golds over here, 3 sulfurs, 2 hydrogens. On this side, we have the 1 gold, the 1 sulfur, and the 2 hydrogens. This is another place where that subscriptive coefficient trick will come in handy. I'm going to take the 2 over here to the gold. I'm going to take the 3 over here to the hydrogen sulfide. Now I'll change my product numbers accordingly. I've now got 2 gold, 3 sulfur, and 6 hydrogen. And we can see that by doing that approach, we have taken care of the gold, we have taken care of the sulfur. The only thing we haven't taken care of the hydrogen, and the hydrogen's all in one molecule on the reactant side. I need 6. They come in groups of 2. 3 times 2 gives me the 6 that I need. So again, the real trick here is anytime we see a compound that is more than one element in a group, and that group of elements has multiple subscripts, that's usually where we're going to start the balancing from. So H2S, even though we've got 2 different elements there, there's only 1 subscript. The hydrogen has a 2. Sulfur doesn't have anything. So we're not going to use that as our base. This at least gives us a start. All right, we've got one more example. And that is, we've got PCl3, reacting with hydrogen again to make PH3, phosphorus trihydride, and HCl. So setting up our right, so setting up again, we've got phosphorus, chlorine, and hydrogen on the one side. There are 1 phosphorus, 3 chlorine, and 2 hydrogen over here. On the other side, we've got phosphorus, chlorine, and hydrogen again. There's 1 phosphorus, 1 chlorine, and 4 hydrogens on this side. 4 again coming from 3 from this molecule, pH3, 1 from the HCl. 3 plus 1 is 4. So if I look at it going across, we see that phosphorus is even. Chlorine and hydrogen are not. Now, if we follow our rules, we know that the chlorine is going to be the one that we attack first. And the reason we attack the chlorine first is because it's not hydrogen. Hydrogen is in multiple products. We're going to try to avoid balancing it to the very end and hope that everything kind of works out. So from that standpoint, I've got 3 chlorines over here. Just the one over here, I'm going to make 3 HCl's as a result. 3 HCl's are going to give me my 3 chlorines. That's going to balance out the chlorine. My hydrogen, I now have 3 in pH3, 3 from HCl. 3 plus 3 is 6, which means I will need 3 hydrogens over here to balance it out. Now, if you don't follow that approach, you can spin yourself in a great number of circles trying to get everything to balance out in this particular problem. So one of the things I always tell my students when we're balancing equations is that we have to be very mindful of kind of following the steps and doing them in the proper order at the proper way. If we don't, if we just kind of haphazardly guess, okay, I think I'm going to put a 2 here and see what happens. I think I'm going to put a 3 here and see what happens. You might eventually get to the answer that way. They're going to take a lot longer to do it, because there are a lot more directions that you can go that can make things very difficult. All right, so any questions about any of these 3 examples? Yara. So we had 3 H's from the pH3, 3 times 1, because there's 1 hydrogen in each HCl, and there are 3 HCl's. So 3 times 1 for that. The 3 plus 3 gives me my 6. You're welcome. Other questions? All right, so let's move off of balancing equations and talk a little bit about the chemical reactions themselves. So when it comes to chemical reactions, one of the ways that we can describe a reaction is based upon something called reaction rate. That is how fast the reaction actually goes. One of the really interesting kinds of paradoxes with regard to chemistry is that just because a reaction can happen doesn't mean that it'll happen fast. In the world of general chemistry, we call that the difference between thermodynamics, that is, will a reaction run, and kinetics, which is, will a reaction run fast? Now, most of the time, we can help a reaction along by doing some things to it to increase the reaction speed. Because the longer a reaction goes, the less likely it is to give you 100% of what it is that you're looking for. The more likely it is that we're going to end up getting a side reaction or an incomplete reaction of some kind. And so reaction rate ultimately depends on at least 7 factors. We're going to present 7 here. There are more, but these are the 7 most common. First is the nature of the material. This is where our understanding of hazardous materials comes in. Do we recognize that this material is an oxidizer? do we recognize that this material is flammable by its definition? What does its NFPA 704 placard look like? We have a yellow diamond with a 4 in it. We have a yellow diamond with a 1 in it. Those kinds of things make a difference. Second, the subdivision of the reactants. What are they? How are they mixed together? Are they solids? Are they liquids? Are they gases? Are they currently being held separate from each other? Are they in one big container together? Those are all things that make a difference. Their state of aggregation. Again, are they a solid, a liquid, a gas? How are they held together? If they're a solid, are they finely divided and really fine powders? Or are they big blocks, like a giant block of metal? 30 pounds of magnesium are going to react differently depending upon how they are put together. If I have it in one big cube, it's going to be reactive. The reaction of that 30-pound block is going to be a lot less than if I pound it out into a fine sheet or if I pulverize it into fine powder. Concentration. This is more when we deal with things that are in solution. How much stuff is there? One of the great things about kinetics is it's often very concentration dependent. Reactions go faster when we have more stuff available. Activation energy. All reactions have activation energy. That is the amount of energy that is necessary to kickstart the reaction. For example, we know that the material on a match is flammable. But a match doesn't light on its own until we strike it. And the striking of a match involves some frictional force, usually tied to the nature of what is on the matchbox itself. Now, if you have strike anywhere matches, the match head themselves has usually some powdered glass in it, something to give it a rough abrasive surface so that when you strike it against something, that abrasion causes enough friction, causes enough heat to get the match to light. But a match doesn't light on its own without that striking force. That's activation energy. Now, just because you have activation energy doesn't mean that the reaction is necessarily slow or that the reaction requires a whole bunch of energy. But all chemical reactions need a little bit of a boost to get started. You know, I've got 5 children. Bedtime is always a really interesting kind of endeavor because they all are tired. They all need to go to bed. Sometimes they even want to go to bed. But you still need to do a little bit of kicking to get them to go up those stairs to get into their bed. That's activation energy. All reactions want to go to their natural end. Some need a little bit more help than others. Now, part of that help can be these last 2 factors. Temperature. If I raise the temperature of a reaction, that is going to insert more energy into that system. And that can be enough to help overcome activation energy. So simply raising the temperature sometimes is enough to get the reaction to go faster. And catalysis works in kind of the same way. Instead of raising the bar, raising the overall energy inside of the system, it kind of works on the opposite direction. It lowers the activation energy. So it makes the reaction go faster because it doesn't have as much of an energy field to climb. My kids only had to go up 3 steps instead of 7 steps. They might be a little bit more inclined to get up the stairs a little bit more easily. Probably not. That might be where my analogy falls apart a little bit. But nonetheless, it's easier to climb 3 stairs than it is to climb 7 stairs, or 11 stairs, or 35 stairs. We think about that staircase's activation energy. What a catalyst does is says, you know what? We're going to do this reaction differently. You don't need to do these steps here. You just need to do these ones. And that makes the reaction faster. If I couple those things together, then I can really do a lot of good things, a lot of potential reactions. So here's an example of our concept of surface area. In these 3 containers, I have the same amount of flammable liquid. But you can see that the more I spread out that flammable liquid, the more the reaction proceeds. This far panel on the right is going to run out first. The reaction is going to finish in that panel fastest compared to the other 2. Not because the materials are any different, we just have exposed more of it to the atmosphere. More oxygen is present, reaction is going to proceed faster. When it comes to combustion, again, we talked about what a combustion looks like from a chemical reaction standpoint. Now let's talk about what it looks like in the real world. Combustion reactions are chemical reactions that end up releasing energy, and those energy releases come in the form of heat, light, and sometimes some other forms as well, but usually heat and light. Sometimes we see some sound, sometimes we hear some things come off it as well, but it's mostly heat and light. And predominantly, we feel the heat much more than we see the light. In fact, depending upon the nature of the combustion reaction, some of the combustion reactions are so energetic that the light that they generate is actually beyond the scope of what we can see with our eyes. Heat manifests itself largely as infrared energy. Infrared is not something that we can pick up. But on the flip side, things like alcohol fires. Those alcohol fires burn so cleanly that at most what we might see is a little flicker of a blue flame, but for the most part, we don't see it. We feel it, but we don't see it. Hottest part of the flame, well, we're talking about a laboratory burner. We're talking about you're going to have the 2 cones. The very tip of that brighter blue cone, the inner cone, that's the hottest part of the flame. Now, if we're talking about a candle, there really isn't a hottest part of the flame. What we tend to see more is that the area right above the candle is the hottest compared to the sides. Combustion reactions are a subclass of a larger group of reactions called oxidation reactions. Oxidation reactions refer broadly to reactions where electrons are being moved from one reactant to another, and usually that involves oxygen, which is why it's called an oxidation reaction. Usually oxygen is involved, and whatever substance is burning is ending up giving its electrons to the oxygen. When we look at combustion, combustion can come in 2 different forms. The first form is something called complete combustion. Complete combustion is when we have sufficient oxygen present. And as a result of that sufficient oxygen, we get complete conversion to carbon dioxide and water. And we usually see these kinds of reactions show up as either an invisible flame. This is especially true for low carbon kinds of fuels like methanol, like ethanol, or we see them as blue flames, like what you see in your Bunsen burner when you burn the methane. These fires can be very hot because you're getting a complete conversion to the products. But complete combustion can be kind of hard to obtain. In a Bunsen burner, we achieve it by basically doing a reaction where we allow a lot of airflow into the barrel of that Bunsen burner right before we ignite it. And similar kinds of things happen in your engine. Most of the combustion in your engine is complete. Otherwise, you'd start to see carbon scoring and other kinds of funk building up in your engine as it was burning up the gasoline or the diesel. So your car has a lot of mechanisms inside of it designed to aid in the completeness of that combustion. But when we don't have enough oxygen present, we end up getting incomplete combustion. Now, incomplete combustion is such that we don't have enough oxygen present. So the chemical reaction starts taking shortcuts. And those shortcuts are designed to continue to break down the fuel, but do it in such a way that it doesn't use up as much oxygen per molecule. So instead of getting carbon dioxide and water, we get those, but we get some other stuff as well. We get an incomplete breakdown of the carbon. We get carbon solid, comes out as smoke. We get carbon monoxide. And depending upon what else is around, we might also get some NOx gases as well. NOx referring to any of the nitrogen oxide compounds that form as a result of incomplete combustion. So this can be nitric oxide, this can be nitrogen monoxide, it can be nitrogen dioxide. Not going to find too much nitrous here, N2O, but nitrogen monoxide, nitrogen dioxide, dinitrogen pentoxide, N2O5, those are going to be much more likely. The reactants, the incomplete nature of this combustion indicates that we're going to get a yellow-orange flame as a result. That means it's less energetic. These fires also tend to burn less hotly. It's not to say that they aren't hot, but they're not nearly as hot as a blue flame. So now that we've discussed kind of the nuts and bolts of the combustion reaction, let's talk about fire. Now within fire, what we have is a self-sustained oxidation. That is, the reaction is occurring, and not only is it occurring, there's enough of it occurring that it continues to feed itself. And the reaction continues to go and go and go, and we end up having a fire that builds and burns and burns and burns. This is designed to keep us separate, again, from that definition of flashpoint that we talked about with liquids a couple of chapters ago. Because a flash is not a self-sustained reaction. It's a momentary combustion chemical reaction that dissipates because there's just not enough fuel to sustain it. Now, when we talk about fire, we end up talking about something called the fire tetrahedron. 4 elements, 4 things that are necessary in order to maintain a combustion reaction. The 4 elements are these. First, fuel. You have to have something to burn. It's the main difference between flash point and fire point, right? The flash point, it ignites. There's not enough there to sustain it. There's not enough fuel vapor there to continue the combustion. So it flashes and goes away. In order to maintain that, we have to have a steady supply of fuel. We also have to have a steady supply of oxidizer. Now, most of the time, oxidizer is going to be coming in the form of oxygen. And if not oxygen directly, then we're talking about compounds that usually release oxygen as part of their decomposition process. So, for example, peroxides. Peroxides, upon heating, will generate oxygen gas. You also need a source of heat, an ignition source. Initially, this ignition source is present to help you overcome the activation energy. But that source needs to continue to be present to continue the vaporization of the fuel, the vaporization of the oxidizer, to keep the reaction going. And then you need a chain reaction, where the combination of those first 3 elements is sufficient that it continues to regenerate itself. It continues to go. We continue to make more fuel. We continue to find more oxidizer. Without that, take away any legs of this tetrahedron, and the flame, the fire, collapses upon itself. I'm sure all of you have done this at some point. You light a candle, you cover the candle goes out. The reason that happens, we're taking out one of the legs of the flame tetrahedron. Before that, all 4 are present. You've got the fuel, the candle itself, the paraffin wax. You've got oxygen from the air around it. You've got heat coming from you lighting the candle. And you got a chain reaction where the heat of that lighting is enough to continue to vaporize the paraffin and continue the reaction. As soon as you cover it up, you cut off the supply of the oxidizer, the reaction stops. Firefighting measures are all about taking away one of these dimensions or another, sometimes multiples of them. So some common characteristics. Flames are exothermic. Flames are exothermic, meaning they generate heat. And part of that heat generation is that we get either visible light, yellow, blue, or we get infrared light, which we feel primarily just as heat. The products that we see depend upon whether we are looking at complete or incomplete combustion. All fires occur with vapor states. So we talked about this a little bit when we talked about flammable liquids. The liquid itself isn't what's burning. When we talk about solids, The solid itself isn't what burns. It is that the heat of the reaction is causing that solid material or that liquid material to vaporize. And you can prove this to yourself at any time. Take any solid object that is on fire and try to cut it in half to see the fire on the inside. You'll never find it. Someone made a good point when we talked about this initially. If I'm burning a solid, you have to have the exposure to the oxygen. Inside of the solid object, there is no oxygen. So how would a fire form in there in the first place? And that's a really good, relevant point. Fires burn in a V-shaped pattern. Lyric had asked me earlier about the hottest part of the flame. Well, the reason that the flame creates that triangle shape has everything to do with convection. So we talked about convection earlier. The idea that heat rises. Well, as that heat rises, eventually what happens is gravity starts to act on it. And so what we'll see is as we come away from the flame itself, we'll start to get those convection currents as it kind of cascades down. And so we'll get a tall point of the flame where the convection is going straight up still. And we'll get kind of a curvature as that gravity starts to impact the movement of that gas, the movement of that heat. So that creates this conical kind of shape. And that's why we end up getting that V-shaped pattern. Now, the reason for the secondary cone has a lot to do with intensity. There is a secondary intensity of the burning inside of the middle of that flame that creates that secondary cone. And that's why that cone itself is so hot. And the tip of that cone is kind of the hottest part because that's where the heat is the most concentrated. That's where the convection current is the most upward, most straightforward. In the absence of heat, or excuse me, in the absence of gravity, flames look a little bit different. I'll see if I can show you a picture here at the end. Let's finish this one off. You have to have appropriate fuel to oxygen ratio. In your car engine, this is what the carburetor's primary job is, to introduce extra air into the engine so that the reaction can burn as completely as possible. Absent that, we have one of two problems. If we get too much air in there, then basically the air separates all the fuel molecules from each other, it chokes itself out. We call that a lean fuel-to-air mixture. There's too much air, there's not enough fuel, we can't get a proper self-sustaining reaction. The opposite's true as well. If not enough air gets in there, we've got all of this fuel vapor, but not enough oxygen to burn it all, we either get incomplete combustion or non-combustion. If incomplete, we get all those side products, the smoke, the carbon, the soot, carbon monoxide, all those toxic gases. With non-combustion, we basically just get hot fuel vapor that works its way through the engine. That's not good either. So we will finish this last part of chapter 5 on Wednesday. Wanted to end today, because I know there's a lab question about it. those of you on Zoom, I'll show you the series to you. This was actually an experiment that was done on the space station. The question was, how does a flame burn in zero gravity or microgravity compared to down here on Earth? As I mentioned before, with normal gravity, we get that conical shape primarily from the direct result of the heat rising and gravity acting on that heat and creating that somewhat of a convection current. That's what gives us that conical kind of shape for most flames. In microgravity, because we don't have that downward force, we see a much more even burn. There's no gravity acting downwardly, so we see much more complete combustion, very, very close to that wick of the candle. That's the main difference. So I'll leave you with that thought, and have a good day today. I'll see you on Wednesday.